Okay, so now we're going to apply the theorem to actually try to solve a problem or try to compute an integral. So we have this vector field, and C is the union of the top half of the circle of radius 1 centered at the origin with the line segment from 1, 0 to 2, 0. So basically, and I didn't say it, but I'm giving it counterclockwise orientation. So this is the top half of the circle, and then this is the line segment. I better do this in a different color. Okay, so this is the line segment. So this is -1, 0, and this is 2, 0. And we are transversing this in what would be the counterclockwise direction. And so what we want to do is try to apply the previous theorem. To do that, we have to figure out, does f, is this the gradient of some function? So if we take the the y derivative of y cosine xy, we see that this is equal to cosine of xy minus xy sine of xy, and the partial derivative with respect to x of x cosine xy is equal to cosine of xy minus xy sine of xy. So since these two functions are equal to each other, this tells us there is a potential. Okay, so this is what we're going to do. So we're going to say that f of xy is equal to the antiderivative of this first function with respect to x plus some function of y. So the antiderivative of cosine xy with respect to x is sine of xy, and now we add in an arbitrary function of y because this is what we need, because when we take the derivative of this function, we're going to get y cosine xy plus 0. Okay, so how can we figure out what y is? Well, we know that the partial derivative of f with respect to y is equal to x cosine of xy plus 2y, but we also know that this is equal to f, and the derivative of that with respect to y is x cosine of xy plus phi prime of y. Okay, so now notice that we can cancel stuff. We can cancel the x cosine xy, that x cosine xy, and what we end up with is phi prime of y is equal to 2y. And remember, if we had gotten phi prime of y is equal to some function of x and y, we would have made a mistake. But we just have phi prime of y is equal to a function of y. That's what we want. So if phi prime of y is equal to 2y, this means that phi of y is equal to y squared plus some arbitrary constant. So in other words, f of xy is equal to sine of xy plus y squared. And we just want any function that satisfies the gradient of f is equal to big F. We don't care what it is, so the easiest is just to take that constant equal to 0. So in other words, what we've said is that f of xy equals sine of xy plus y squared. That function is a potential for this vector field.